Hello. Before we get started on this hydrolysis, did I spell it right? Yep. Hydrolysis list, how we're going to hydrolyze these carboxylic acid derivatives. I just want to mention that there was, you might have heard some heavy breathing at the beginning of the first video. That was not, it definitely wasn't me because I was talking while there was heavy breathing. That was my cat. But she's now asleep. It looks like organic also puts her to sleep as well. Let's talk about hydrolysis now, because we're moving on to the carboxylic acid derivatives, and you should be able to rattle them off quickly, right? Acid chloride, anhydride, ester, amide, from the top of the totem pole to the bottom. And we're going to see reactions. And, if we're going to learn the hydrolysis of an acid chloride, we're going to learn the hydrolysis for the other derivatives. If we're going to do a nucleophilic substitution on an ester, we're going to do a nucleophilic substitution on all the other derivatives to compare. Eventually, we'll have such a large network of reactions, we can go, and this is jumping ahead a little bit, we could go from an ester to an amide, to an anhydride, to an acid chloride, to a nitrile, back to the acid chloride, to the amide. And that's great. That's the goal of synthesis, to be able to go from functional different classes of molecules with these reactions. Let's take a look at the hydrolysis. I said this is simple, huh? Okay. Oh, great. We have tips. Thank goodness, because I don't think it's simple unless you use these tips, like drawing dots and cut lines, because hydrolysis, again, is you cut or you lyse with water. Okay? We're going to push water in there and we're going to cut something. And so the dot that I'm talking about is the dot on the acyl carbon. Okay, let's not call it carbonyl. Carbonyl, I want to reserve it just for aldehydes and ketones. So that carbon of the carbon-oxygen double bond is called an acyl, right? Acyl carbon, ACYL. And we're going to put a cut line. Why did I use purple? Cut line right here. We're not drawing the mechanism. We went over the mechanism in class, and you have other chances to practice it on the ACE. I want to know what are the products. Oh boy. Read your directions. It says draw both. What does that mean, draw both? I don't know. Oh, you know what it means? We're going to have the left side of the molecule and the right side of the molecule. Okay. If you're uncomfortable drawing the fill in the products without studying the mechanism, okay, go ahead and stop this video and go over the mechanisms we went over in class, maybe 2 or 3 times each until you can draw it from memory. Okay, but eventually you're going to need to be able to take some shortcuts, because a lot of problems on the exam, I'm just going to ask for the products. Okay, and so lyse is you're going to cut, and the dot, it becomes a carboxylic acid. That's the definition of a carboxylic acid derivative, that you could hydrolyze it to make a carboxylic acid. This derivative, again, acid chloride. Okay, can you beat me? Ester. Amide. Nitrile. Nitrile is number 5. I only did 4. 1, 2. We're missing one. Oh, it's over here on the right, anhydride. So the totem pole is not really has all the members. Again, for reactivity, most reactive, second, third, and fourth, a tie between these two. First, you only need water. They're so reactive, you don't need any help with acid or heat. Just use water for the acid chloride and the anhydride. All right, I talked a lot. I don't even have a second product here. The kickout group was chlorine, and it picked up a hydrogen when it deprotonated the molecule in the mechanism. Again, we're not drawing the mechanism in this video, but I wanted to show you that, remember how I said we have lysed with water? Well, we shoved in water here, OH, H, okay? And technically, this dot was attacked with water first, like literally. What color should I use? Orange. So literally, this is the first step of the mechanism. Okay. Anhydride. Let's use the dots and the dotted line. Ooh, interesting. Because this dot on the left is a different cut line than if I put in this dot, okay? So you have to choose. The thing here is that, let's do the one on the left. And I hope I can convince you that if your classmate put a dot on the right, they would get the same products. But by putting the dot on the left of this oxygen, the cut line is here. And so you remember what happens to the dot? That ultimately is the carboxylic acid. Dot, carboxylic acid. And your kickout group was this, O minus, which eventually picked up a hydrogen. Okay, where did it pick it up from? Water, right? Water, when water attacked, it had 2 hydrogens. Now it only has 1, this oxygen. So that other hydrogen went to this molecule here. You have 2 carboxylic acids, okay? And so if you had cut here, you would still have this acid, and you would have this acid. You have the same 2 products, okay? The way I cut it, the H2O was there and there. Again, since you're making 2 carboxylic acids, it doesn't matter if you think the left side is a carboxylic acid or the right. They're both sides ultimately become carboxylic acid, so it doesn't matter if you cut here or here. And, you could pause the video or later, cut here. Cut here and do the same thing. Add an H and an OH. You'll get the same products. All right. Cut. I could feel some of you are maybe bored. That's good, right? This is hopefully getting so redundant, right, that it becomes very easy to remember. Dot and dotted line, okay? The left side looks like, the left side has a dot. So the left side is the one with the carboxylic acid. The right side is the alcohol. Okay. And the boxes still work for esters, right? We have an ester, hydrolysis, they're still here. The boxes don't quite work when one of your products gets protonated and it becomes charged, because we added an extra hydrogen. And so we're going to see that in the next case. Amide, dot. Again, if you want to pause the video, please see if you can do this on your own first. All right. If I do the water trick, okay, let me do the water trick and show you what I mean, that it's not going to work out as cleanly as we hoped it would. So the water trick is this, right? You add an OH to the dot, and you add another H to the group that got kicked out. So here we do have water. Okay, so I'm going to put a square, but I'm going to erase it later. H, or OH and H. One of the H's on the amine. So that's water. But the thing is, this molecule right here is a base. Nitrogen-containing molecules are basic. Like, what's the basic molecule that has nitrogen? We worked with it in lab, right? Caffeine. Caffeine used a lone pair to pick up a hydrogen. Same thing here because we're under acidic conditions. So this plus this gives me a protonated amine. And the easiest way to draw that, and now I have to get rid of the boxes. Can I get rid of the boxes? There we go. The easiest way to do that is, is to, maybe it's not so easy. Change that into, okay. Start all over. H3N. And that's nitrogen with 4 bonds, positive. Okay. Just watch out, right? Put a little note. These are your study sheets. And so if you won't need to remind yourself on the study sheet over and over again, watch out. When you hydrolyze an amide under acidic conditions, you got to protonate that amine. And so it's the same thing with nitrile. Your dot is this carbon here. Do you see that? So again, I don't like drawing it on the letter C, but I'll do it here. Your cut is actually that. So you have a naked N, naked letter N. That N, it had to have left as NH3. And it's neutral, but it picks up another proton from HCl. Just make it positive, okay? Make it a nitrogen with 4 bonds. And stops, right? You're not going to protonate it a second time to make it +2, right? You know what a protonated amine should look like. And the other side, the left, that is your dot, okay? And yes, again, that dot is the carboxyl group. That carboxyl group is pretty easy to see when you have acid chloride, ester, and amide, and even anhydride. This C doesn't have any oxygens. So in the mechanism, water had to attack twice because you have 2 oxygens that you had to have added. Class 12. Class 12 is saponification. So this is the most recent handout because we have base and we have ester. Saponification. How to make soap. It's an ester, by the way. So we're going to have a different product, it looks like, even though we both start here and here with an ester. So look at your ester hydrolysis products. Carboxylic acid, alcohol. Okay. That's initially what you actually get. And so without taking shortcuts, there's your dotted line and your dot. Initially, you do get this. Okay, plus, you plus HO minus. No, sorry, HO, the alcohol. Now, you're under basic conditions. That's super important because if you have any acid, you're going to have an acid-base reaction. The thing is this. You potentially have 2 acidic hydrogens. I mean, you do. But one is more acidic than the other. And those of you who had me for Organic 1, you used quite often the pKa table. The pKa table tells me a regular alcohol is a pKa of 15.5. The carboxylic acid is 5. So you tell me which is a stronger acid. Okay? And so what happens, and I wouldn't draw this on the exam, but I want to show you that the real final product is this getting deprotonated. And you have the carboxylate. So take a look at that. Watch out, there's a charged molecule here. Well, now we have the opposite. We have a negatively charged. Watch out. For saponification, make carboxylate. Spell it right. Carboxylate. ATE. Anion. Okay. Is that simple? It should be. Simple, fill in the products. The harder one is when you hydrolyze and it ends up breaking your necklace or your bracelet or your hair tie. Because look where the cut is now. Oh, dang it. I made a mistake. This is going to have two different products. Wait, is it going to have two different products? And that's an anhydride, correct? What do you get when you... what do you get when you hydrolyze an anhydride? You should get two carboxyl groups. See, I have it. I literally have it right here. Two carboxylic acids. Sorry, right here. Two carboxylic acids. Or you could just say two molecules that both have a carboxyl group. That's what I was about to write. Two carboxyl groups. They may be connected. So I don't like saying two carboxylic acids because your two carboxylic acids may actually be on one molecule. Let's say two carboxyl groups in this case because look where I'm going to cut. It doesn't matter if it's this dot or this dot. Okay? And so let me do the bottom. Okay? And you're going to cut this. What happens to this dot? Remember what happens to this dot? You add an OH, like we did up here. The dot has an OH. And what happens to this O right here? It picked up an H. Okay? Again, it is assumed that, maybe not now, but if you're really having trouble visualizing what the product is and you don't understand how I'm using the tips and the tricks, then you may need to do the mechanism 2 or 3 or 4 times. Because at this point, you have to take it on faith that, yeah, there will be an H on this oxygen, okay? And when you do the mechanism once, you'll see that there is. Now, without drawing the mechanism, could you tell me where that H came from? That's a little bit hard, right? Because you're trying to visualize every step. But if you drew the mechanism, you could definitely tell me, when did this oxygen over here pick up an H? When did this dot get an OH? Okay? Okay, so enough talking. We have to literally erase this bond right here. So look how I'm going to draw it. I'm going to try to draw it with all the atoms pretty still. Whoops, that's not the dot. The dot is actually down here. And the dot is the carboxyl group. Okay. I yelled at someone for not putting in an angle, so let me put in an angle. Okay, it's going to be crowded, I think. And so that takes care of the dot. On the other side, we do have the C, double bond O. My goodness. And then we have this, getting in trouble with the angles again. We have this O, and then it picks up the H. And so we added what? We added that OH and that H. Same thing we did up here. See, I put a box on the OH and the H. Let me redraw this, okay? Now I know what I have to draw. I know which bonds to swing out of place, I think. We're gonna go down this way. And then we have the dot here. Okay, that's the same number of carbons, I think. It's not the same number of carbons. I added one by accident. Okay. The dot is, see, I need to use a dot. Dot is right there. That's where the carboxyl group goes. Okay. The last two. Man, this, what happened here? I'm gonna change this. Or, it would have been changed by the time I get this handout. This should be in the middle because I have two arrows, one to the left and one to the right. Anyway, this is great because now we're comparing the two ways to hydrolyze an ester. Acid-catalyzed and class 12 saponification. So let me do saponification here. If I'm going too fast, pause the video or, rewind it. Do you guys use the word rewind? It's not a cassette. Go back 10 seconds. Okay. Saponification, I have experience, is the one where you get the carboxylate. Actually, let me put a circle around these two because I don't want you to get confused. Right? These two. Those are the products. So I need a carboxylate for saponification. The carboxylate, I hope you know it's obvious, it's going to be on this dot, O minus. And what did the other O turn into? An OH. So I'm counting here one. Let's not use dots. I don't know. We have a CH2, CH2. 1, 2. Okay, and so 1, 2. This is 1. This is 2. We have an O right there. I almost made a mistake. I almost put the O right here, but I would have lost that carbon. And your H is there. That's saponification. It has the carboxylate. For the acid catalyzed, everything's neutral. And we have the carboxylic acid, neutral. Hope that's obvious. And the alcohol, neutral. See the difference? Okay, last one. We know that this N, right here on the right of the dotted line, that N has to have enough hydrogens for it to be a +1. And the dot is a carboxyl group. Dot is a carboxyl group. The nitrogen, how am I going to draw this? The nitrogen is going to be +1. So we have this. Again, we have that. One CH2, the second CH2, N. But that N also has this ethyl group. So you're just copying ethyl. Doesn't matter if you draw it up or down. Okay? So just try to make it look good with the correct angles. And then now comes the H's. It left the molecule like that. But because you're under acidic conditions, it picked up another proton to become protonated. That's your final product. And those, I guess we call this a little bit harder, but it's the same idea, the dot and the dotted line, and you're adding water, okay, like here and here. But for the ones that charged, your count gets kind of messed up, right? This nitrogen over here, it picked up another H, one more than you thought you would have had to have, because now you realize that it's under acidic conditions, and amines will be protonated under acidic conditions. Okay, zoom out. Not a bad study sheet here as well. Every hydrolysis, even the saponification, which is base, we call it base mediated instead of catalyzed because it's not technically catalytic. Catalytic means you add a little bit and then you regenerate the catalyst. Well, here, the base, this base right here, this OH minus, it literally gets incorporated into the molecule. This O right here is this O over here. It's just that the H is lost because acids are acidic and you're under basic conditions. Okay. Not bad, right? If you could have, this sheet and the sheet before it, pretty early in the weekend and study off of it. Essentially, this is a review. This is a review of our first 5 classes? First 4 classes of this next exam. This next exam is only 7 lectures. The last exam was 8. Okay, so after Friday's class 12, we only have 13, 14, 15. Okay, so this is the halfway point. This is the halfway point that you have to be ready for the second half next week.